Okay, so Rankine cycle has 4 components. They are a boiler, and what else? Turbine, and condenser, a pump. The direction of the cycle is going to be this way, from boiler to a turbine, and turbine to a condenser, from this condenser to a pump, from this pump to the boiler. And the exit of the boiler is called number 1. The exit of the turbine is number 2. And number 1 is again the inlet of the turbine. Number 2 is the exit of the turbine and the inlet of this condenser. Number 3 is the exit of the condenser and the inlet of the pump. Number 4 is the exit of the pump and the inlet of the boiler. And we have a heat transfer into the boiler, Q in. If it is steady state open system, Q dot in, so that we can increase the enthalpy of this steam from number 4 to number 1. And at the number 1, and from this turbine, we produce this power W dot out, but this is from the turbine, so we are going to say W dot T. And in this condenser, we are going to reject any waste heat to the outside, so we have Q dot out. And in this pump, we are absorbing power, that is pumping power, W dot T, so that we can maintain this Rankine cycle. Then let's analyze each component thermodynamically. So how can we do that? We can use the energy balance equation. The general energy balance equation for steady state open system, then we have Q dot in plus W dot in plus M dot at the inlet. This one has enthalpy, kinetic energy, and potential energy, but we are going to neglect them. This is going to be Q dot out plus W dot out plus M dot at the exit. This one has specific enthalpy, kinetic energy, and potential energy. That looks weird, like the flight is taking off. Anyway, so then we can neglect kinetic energy change, potential energy change, and we can apply this energy balance equation for this boiler first. So in this boiler, we have a heat transfer into the boiler. So we have this one, and the inlet is number 4. So this one number 4, and the exit is number 1. This one number 1. So the energy balance equation is Q dot in plus M dot. By the way, there is only one inlet and one exit at each component. Therefore, the M dot is going to be constant. So there's no M dot number 4, M dot number 1 is going to be just M dot. So M dot H4 is M dot H1. So this is the energy balance equation for this boiler. What about this turbine? This turbine, the inlet is number 1. This time it's going to be number 1. exit is number 2, this one is number 2, this one produces power. So we have M dot H1 is turbine power, W dot T plus M dot H2, that is turbine. Need to stay, this one is boiler, B turbine, T, then S, no. Then let's look at this condenser. The inlet is number 2, the exit is number 3, and it has a heat transfer from the condenser to the outside. So we have this one. So M dot H2 is Q dot out plus M dot H3. That is this condenser, BTC, Bitcoin. Then this pump, we have W dot in, which is pump. The inlet is number 3. The exit is number 4. So this one is W dot P plus M dot H3 is M dot H4. That is pump, ETCP. I don't know. Okay. So that's how we get the energy balance equation for each component. Then, how can we determine? So this is the energy balance equation as we studied in chapter 4. Then what we studied in chapter 5, we studied how do we evaluate the performance of a system. So how can we evaluate the performance of this Rankine cycle? By using efficiency. So what is efficiency? This efficiency is desired output over required input. So what is desired output? We want to produce turbine power, and we want to consume pumping power so that we can run this cycle. So the desired output is going to be net energy and net energy transfer by work over required input, what we need to provide to produce this net power, Q dot in. So we need to either burn some fossil fuel or nuclear reaction or concentrating the sunlight to obtain high temperature heat. So this is how we determine the thermal efficiency of the system. By the way, this net power is going to be W dot T minus W dot T over Q dot in, and according to this energy balance equation, this W dot T is here, which is W dot T is M dot H1 minus H2, right? If you move this one to the other side, then yeah, we can do that. So we can replace this W dot T with M dot H1 minus H2, M dot H1 minus H2. What about this pumping power? The pumping power is here, so why don't we move this one to the right-hand side, and we get pumping power W dot T is going to be M dot H4 minus H3. So we can say this W dot T is M dot, am I recording this one? Yeah. M dot H4 minus H3. divide by Q dot in. Or where is Q dot in? It's right here. So why don't we move this one to the right-hand side? Q dot in is M dot H1 minus H2. What? H4, my bad. So this is going to be M dot H1 minus H4. So the thermal efficiency is going to be, by the way, we have M dot, M dot, M dot. What do you want to do? As an engineer, we like simplification. So we can neglect them. We can cross them out. So that's how we determine the thermal efficiency. If you can determine the specific enthalpy at each state, then you can determine the thermal efficiency. By the way, for this Q dot out, let's move this one to the left-hand side. Then Q dot out is M dot H2 minus H3, just for your information. So that's how you can analyze a Rankine cycle. There's one more, which is called BWR. That is back work ratio. Then, by running this Rankine cycle, we are producing turbine power, but some of this turbine power is going to return back to this Rankine cycle to run this pump, right? Because we need to run the pump to maintain this cycle. So a small portion of this turbine power that is produced by this Rankine cycle is going to be used to run this pump. So how much, the power that we produced by the turbine is going to be used for the pump? That is back work ratio. How can we calculate that? W dot P, pumping power over turbine power. Then how do you determine pumping power? It's right here. M dot H4 minus H3 over turbine power. It's right here. M dot H1 minus H2. So the back work ratio is going to can be calculated by this. In a typical Rankine cycle used in most power plants in US or any other the world, this value is close to 1 or 2%. So you can see, the back work ratio is pretty low for the Rankine cycle. But this is just for the Rankine cycle. So if you, come up with, the another heat engine, such as gas turbine, like a Brayton gas turbine, where we use for jet engine, or where we use for, the power plants that don't use any steam, the back work ratio go up to 40 to 60%. But we are going to talk about that later in chapter 9. Okay? In this chapter 8, we are going to focus on vapor power cycle. In chapter 9, we are going to talk about gas power cycle. The main difference is that the working gas in this chapter 8 is going to be steam. The working gas, if the working gas is other than steam, such as, the carbon dioxide or sodium or fuel air mixture and any other systems other than the steam, we are going to study them in chapter 9. Okay. So this is how you can analyze an existing Rankine cycle. Then what we are going to study today, we are going to study, how we can, model this Rankine cycle so you can design one. So to do that, we need to simplify this Rankine cycle by using ideal Rankine cycle. We are going to make some assumptions because the actual Rankine cycle is going to be very complicated. So we cannot analyze them by hand, we need to rely on computer simulation. So then, is there any way to simplify Rankine cycle? Yes, there is. That is called ideal Rankine cycle. And to do this ideal Rankine cycle, we need to make some assumptions. Why? Because we want to simplify Rankine cycle. So let's see what kind of assumptions that we are going to use. So we are going to assume that there is no, the friction in the system. There's no energy loss in the system. And we assume that turbines and pumps are adiabatic. That means that they have a good insulation, so we are not losing any energy. And without irreversibility, that means that there is no energy loss due to friction or heat transfer. So that means they are ideal, which means ideal turbine, ideal pump. In thermodynamics, ideal means isentropic. So we assume that our turbines are isentropic, our pumps are isentropic. That means entropy does not change. So with that assumption, and there is one more, and we assume that the boilers and condensers are constant pressure processes. So two assumptions. We assume that boilers run at constant pressure, condensers run at constant pressure, turbines run an isentropic process, and pumps are isentropic pump. So based on that assumption, let's study this Rankine cycle. So we are going to say this pump and this, we are going to say this boiler runs at constant pressure. Constant pressure. This condenser runs at constant pressure. What does it mean? The pressure at number 1, which is P1, is the pressure of the boiler, should be the same as the pressure at the inlet. So P1 and P4, they should be the same. What about this condenser? Is a constant pressure process. So P2, the inlet pressure of this condenser, and P3, the exit pressure of the condenser should be the same. So when we say Rankine cycle, there are only two pressure values. They are boiler pressure and condenser pressure. So we can divide this in half and saying that there's one pressure, which is the boiler, there's another pressure, the other pressure, which is the condenser. So boiler runs at high pressure, condenser runs at low pressure. Okay? And this pump and turbines are isentropic turbine, isentropic pump. If we make those assumptions, then we can, analyze them. We can analyze them in this simple TS diagram. What is that funny? What? 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 Okay. So let's do this analysis. So in this ideal Rankine cycle, we can study them on this TS diagram. So if we study them on this TS diagram, we have two pressure values. One is the boiler pressure, the other one is condenser pressure. So the boiler pressure is high. Sorry, cannot see them. So the boiler pressure is high and condenser pressure is low. So we have one pressure value P, then TS diagram looks like this. And we have another pressure value, which is for this condenser. So this is boiler pressure. And this is condenser pressure. And our assumption is at the exit of the boiler. So this is how a boiler works. So you have a tank of water, and we are going to heat this water, so the steam comes out from this boiler at the exit. So what is the phase change process of this steam? It should be right after evaporation, so it should be saturated vapor. So this is the exit of the boiler, which is number one. So there's number one. And this number one enters this turbine, and what's going to happen in this turbine? It's going to expand. Expand in what condition? Isentropically. So turbine is isentropic system, so S1 is the same as S2. And this pump is also an isentropic pump, so S3 is S4. So we have an isentropic process from high temperature to a low temperature. So we have isentropic process. This S remains constant. So here is S1, which is the specific entropy at the inlet, and S2 is going to be the specific entropy at the exit. So number two, the exit of the turbine is going to be right here, number two. So this turbine process is going to be from number one to number two, this vertical line. Why this vertical line? Because entropy remains constant from boiler pressure down to the condenser pressure. Again, this boiler is maintained at high temperature, high pressure. This condenser is maintained at low pressure. So both are constant pressure processes. That is the assumption for this ideal Rankine cycle. And then in this, so that's a turbine and condenser. Condenser runs constant pressure process. That means pressure P remains constant. If the pressure P remains constant, that condenser process should be on this line. And what's going to happen in this condenser? Losing heat to the surroundings. So heat is removed from this condenser. Therefore, we are going to go to the left-hand side, to the right, and to the left. On this line, because P remains constant, until all the liquid, all the vapor becomes liquid. So number three is going to be saturated liquid. That's number three. And then what's going to happen in the pump? So this number three enters the pump. This pump runs isentropically. So it should be a vertical line when specific entropy S remains constant. Then pressure goes up in the pump until pressure becomes the boiler pressure. So which is this line. That is number four. And in this number four, the steam receiving heat from the source of the heat in the boiler, so its temperature goes up. From compressed liquid, it becomes saturated liquid, it becomes saturated mixture, and finally at the exit, it's going to be saturated vapor. So it can be a cycle in this way. This is Rankine cycle. Process 1 to 2 is going to be entropy remains constant. It is going to be isentropic. What's going to happen in the turbine? So this is a turbine process. Isentropic expansion. Then what about process 2 to 3? So this is condenser 2 to 3. From 2 to 3, it's a condenser. So what's going to happen is constant pressure and heat is removed, heat rejection. And process 2 to, that's a process 2 to 3, this one. And process 3 to 4, that is this pump from 3 to 4. That's an isentropic pump. So it is isentropic. What happens in the pump? Pressure goes up. Isentropic compression. And finally, we have a 4 to 1, process 4 to 1, that is constant pressure. Heat is added to the system, heat addition. So there are 4 processes by turbine, condenser, pump, and boiler. So that's what happens. So what you need to know is when we say Rankine cycle, this Rankine cycle consists of 4 components: boiler, turbine, condenser, and pump. And these are the energy balance equations for each component. And these are how we can evaluate their performances: thermal efficiency and back work ratio. And this is how we can simplify this Rankine cycle, and that's called ideal Rankine cycle. And this is the TS diagram in the Rankine cycle. Okay. Then we are going to study this TS diagram to learn how we can improve this Rankine cycle. So basically, the energy balance equation, the thermal efficiency, according to this, the equation, the thermal efficiency can be determined by W dot net over W dot in, right? So the thermal efficiency can be determined by W dot net over Q dot in. But if you remember chapter 5, this W dot net is the same as Q dot in minus Q dot out. So to increase the thermal efficiency, we need to increase W dot net, and to increase W dot net, we need to increase the difference between Q dot in and Q dot out. So in this TS diagram, where is Q dot in? This Q dot in is constant pressure heat addition, so there is Q dot in. What about Q dot out? Constant pressure heat rejection, so there's a Q dot out. So we want to increase Q dot in. We want to increase the process 4 to 1. We want to decrease Q dot out. We want to decrease the process 2 to 3. So where is the 4 to 1? This one. And where is 2 to 3? This one. So we want to increase 4 to 1 and we want to decrease 2 to 3. What does it mean? So we want to increase this one, we want to decrease this one. So basically, if you can increase the enclosed area, then you can increase the W dot net. In other words, this enclosed area is W dot net. So if you want to make this Rankine cycle more efficient, one way we can do is we can increase the enclosed area. Then how can we increase the enclosed area? First, what is this, what is this line? This line represents condenser pressure. So if you decrease the condenser pressure, then you can increase the enclosed area. So one way we can do is we can decrease condenser pressure. So if we decrease the condenser pressure, then this line forms below here. So this is new condenser pressure, new, then the enclosed area can be increased by this much. Not just by this much, because this is new number 2, this is new number 3. So there's an additional work you can produce by this much. There's a new number 4. So if you decrease the condenser pressure, you can increase the net work production, net power production by this much. So when you look at, the actual power plant, usually the condenser pressure is extremely low, sometimes even lower than the atmospheric pressure, trying to maximize the enclosed area. So that's one way we can decrease the condenser pressure. Okay. And if you learn that, okay, if we decrease the condenser pressure, we can increase the enclosed area. As a result, we can increase the thermal efficiency. Then you can say, maybe we can increase the boiler pressure too. Yeah, why not? We can increase the boiler pressure. Then let's see what's going to happen. If you increase the boiler pressure, this line moves upward. So there's a new boiler pressure. So we are going to design a new boiler which can withstand much higher pressure. So that's a new boiler pressure, P. Then where is the inlet of the turbine? Here. This is new number 1. And then there's a problem. Since it is isentropic turbine, we can increase this much power and this much net power produces. But there is a drawback. If you increase the pressure of the boiler, you can actually lose this much net power. So increasing the boiler pressure is not always improve the thermal efficiency, because we can add this much net power. However, we are losing this much net power. So it's case by case. So decreasing the condenser pressure always, the benefits the thermal efficiency. However, increasing boiler pressure does not necessarily provide higher efficiency. Okay, so there are two different cases. So decreasing condenser pressure is always good, but increasing boiler pressure may not be always good. Then we need to come up with another way to increase the enclosed area. So one way we can do is we can decrease the condenser pressure, but we cannot decrease the condenser pressure, down to, the vacuum or something. There is a limit, right? So we need to find another way to improve the thermal efficiency of this Rankine cycle. But increasing the boiler pressure may not be the option because we are losing this much net power. So one thing we can do is this is the original Rankine cycle. So starting from here, number one, number two, the condenser pressure should be as low as possible. Condenser pressure. This is boiler pressure. And number three, and number four. So it becomes a Rankine cycle. One way we can do is instead of having boiler, instead of boiler, we can use steam generator. Steam generator boiler, they sound the same, but there is a the one major difference. The boiler, at the exit of the boiler, we have a saturated vapor. But if you have a steam generator, we are going to increase the pressure, increase the temperature and pressure of the steam, so we can obtain high quality steam. What is high quality steam? Not the saturated vapor, but superheated vapor. So this is new number one. Then if you use the superheated vapor rather than saturated vapor, then we can add this much net power. So what we did is that the exit of the boiler becomes from phase change process number 4, saturated vapor, to phase change process number 5, superheated vapor. We can do that by introducing steam generator rather than boiler. Then why don't we do that? Because it's going to be a little more expensive, right? So that's one way. And you may remember, from chapter 3, we studied saturation curve, which looks like that. So if you increase the boiler pressure, and there will be one point which is on top of this, the saturation curve, that is called critical point. So one way we can do is we can use supercritical system that will use supercritical water that will add this much additional power, we can produce this. That's another modification. So that's a supercritical Rankine cycle. And the last one is going to be a little bit complicated, which is called reheat cycle. So this one is similar to the turbocharger in system. So we are going to, the split. We are going to divide turbine into two processes. So original Rankine cycle has steam generator, has turbine, one turbine, and condenser, and pump. P goes back here. So we have state number one, the exit of the steam generator and the inlet of the turbine. Number two, number three, and number four. So there are 4 stages. We can use what is called reheat cycle. That means we have this steam generator, and we have a turbine, but this turbine has 2 stages, first stage and the second stage. And we have a condenser and pump. So let's see what's going to happen. First, this steam generator is going to produce high pressure, high temperature, superheat vapor that will go into the first stage turbine, which is number 1. And this steam is going to expand in the turbine. And while it is expanding in the middle, we are going to return this steam back to the steam generator. So receiving additional heat, number 2, is the exit of the first stage turbine, and then going back to the steam generator, receiving additional heat, increasing its temperature, and return back to this second stage turbine, which is number 3, and continue to expand and exit the turbine, number 4, and reject any waste heat, go back to the pump, number 5, and increasing the pressure, and go back to the steam generator, which is number 6. So this is called a reheat cycle. Of course, you can see this is the reheat process. Then why do we do that? Because we can increase the temperature of the steam in the middle, so we can, produce high quality, we can produce, the turbine power much more than the original one-stage turbine. So sometimes, some people say this is the first stage turbine, second stage turbine, or some people like to say this is a high pressure turbine, and the next one is low pressure turbine. So in this case, we have 3 pressure values. One is high pressure, the highest pressure, number 6, and number 1, that's the highest pressure. And intermediate pressure, number 2 and number 3, and the lowest pressure, the condenser pressure. So there are 3 pressure values. Then let's study that on a TS diagram. We still have 3 minutes. There's plenty of time, right? Temperature and specific entropy. So now we have 3 pressure values. So let's see, this is the lowest pressure, and this is the intermediate pressure, and we have the highest pressure. So I'm going to say the steam generator produces, the superheat vapor. So this is number 1. Now this number 1 goes into this high pressure turbine. So it's going to expand in the high pressure turbine isentropically up to number 2. Then, we already lost too much power to produce this, the turbine power. Let's return this back to this steam generator. And what's going to happen? Additional heat is going to be added to this steam. So its temperature goes up and return back to this second stage turbine and continue to expand. Number 3. And once the expansion is done, it goes into the condenser and rejecting waste heat and go to number 3, number 4, and go into pump. This pump isentropically increase the pressure to the highest pressure, number 6, and then go back into the steam generator. So you can see this much additional power can be added by using this reheat process. Then how can we analyze, how can we determine the performance of this Rankine reheat cycle? We can use thermal efficiency, 1 minute thermal efficiency, which is desired output over required input, Q dot in. Then how many desired output do we have? We have a turbine power in the high pressure stage and turbine power low pressure stage and minus pumping power divided by heat transfer in from 6 to 1 plus heat transfer in from 2 to 3. So that's how we can determine the thermal efficiency of this reheat cycle. Then what about this WT, high pressure stage? It's going to be between 1 and 2. So this is H1 minus H2. What about low pressure? Between 3 and 4. H3 minus H4. What about the pump? Between H6 minus H5. What about this heat addition? Between 1 and 6. H1 minus H6. 2 and 3, between 3 and 2, H3 minus H2. So that's how you determine the thermal efficiency of this ideal reheat cycle. That completes everything about ideal Rankine cycle with all possible modifications. So on Thursday, we are going to, the practice a few problems, to solve, to determine their performances of several Rankine cycles. Okay, that's all for today. See you on Thursday. Any questions? No?